Section 17.2, Buffered Solutions. Solutions such as those discussed in 17.1, which contain a weak conjugate acid-base pair, can resist dramatic changes in pH upon the addition of a small amount of strong acid or strong base. These solutions are called buffered solutions, or merely buffers. Human blood, for example, is a complex aqueous mixture with a pH buffered at around 7.4. Much of the chemical behavior of seawater is determined by its pH buffered to about 8.1 to 8.3 near the surface. Buffered solutions find many important applications in the laboratory and in medicine. Composition and action of buffered solutions. A buffer resists changes in pH because it contains both an acidic species to neutralize hydroxide ions and a basic species to neutralize proton, hydrogen ions. The acidic and basic species that make up the buffer, however, must not consume each other through a neutralization reaction. These requirements are fulfilled by a weak acid-base conjugate pair, such as acetic acid and acetate, or ammonium and ammonia. Thus, buffers are often paired by mixing a weak acid or a weak base with a salt of that acid or base. The acetic acid acetate buffer can be prepared, by example, by adding sodium acetate to a solution of acetic acid. The ammonia buffer can be prepared by adding ammonium chloride to a solution of ammonia. By choosing appropriate components and adjusting their relative concentrations, we can buffer a solution at virtually any pH. To understand better how a buffer works, let's consider a buffer composed of a weak acid and one of its salts. The acid dissociation equilibrium on this buffered solution involves both the acid and its conjugate base. The corresponding acid dissociation constant expression is K sub A equals the concentration of acid times the concentration of the conjugate base over the conjugation of the original acid. Solving for this expansion for protons, we have the concentration of hydronium is K sub A times the concentration of the acid divided by the concentration of the conjugate base. We see from this expression that acid, and thus the pH, is determined by two factors: the value of K sub A for a weak acid component of the buffer, and the ratio of the concentrations of the acid or the conjugate acid-base pair. If hydroxide ions are added to the buffered solution, they react with the acid component of the buffer to produce water and the base component. This reaction causes the acid to decrease and the conjugate base concentration to increase. As long as the amounts of the weak acid and the conjugate base in the buffer are large compared to the amount of hydroxide added, however, the ratio of the acid to the conjugate base doesn't change very much, and thus the change in pH is small. A specific example of such a buffer is the hydrofluoric acid fluoride buffer, as shown in Figure 17.2. Figure 17.2, Buffer Action. When a small portion of hydroxide is added to a buffer consisting of a mixture of the weak acid, hydrofluoric acid, and its conjugate base left, the hydroxide reacts with the hydrofluoric acid, decreasing the concentration of hydrofluoric acid and increasing the concentration of the fluoride ion in the buffer. Conversely, when a small amount of acid is added to the buffer, the protons react with the fluoride, decreasing the concentration of fluoride and increasing the concentration of hydrofluoric acid in the buffer. Because the pH depends upon the ratio of fluoride to hydrofluoric acid, the resulting pH change is small. If hydrogen ions are added, they react with the base component of the buffer. This reaction can also be represented by using hydronium. Using either equation, we see that the reaction causes the concentration of the conjugate base to decrease and the concentration of acid to increase, as long as the change in the ratio of the change in acid to the change in conjugate base is small, the change in pH will be small. Figure 17.2 shows a buffer consisting of equal concentrations of hydrofluoric acid and fluoride ion. The addition of hydroxide reduces the concentration of hydrofluoric acid and increases the concentration of fluoride. The addition of hydrogen ion reduces the concentration of fluoride ion and increases the concentration of the hydrofluoric acid. Calculating the pH of a buffer. Because conjugate acid-base pairs share a common ion, we can use the same procedures to calculate the pH of a buffer that we use to treat the common ion effect. However, we can sometimes take an alternate approach that's based on the equation derived from equation 17.5. Taking the negative log of both sides of equation 17.5, we have the negative log of hydronium equals the negative log of Ka times the concentration of acid over the conjugate base equals the negative log of Ka minus the log of concentration of the acid divided by the concentration of the conjugate base. Because negative log of hydronium is equal to pH and the negative log of Ka is pKa, we have the pH equals pKa plus the log of the concentration of the conjugate base over the concentration of the acid. Where acid and base refer to the equilibrium concentrations of the conjugate acid-base pair, note that when base equals acid, the pH equals the pKa. Equation 17.9 is known as the Henderson-Hasselbalch equation. Biologists, biochemists, and others that work frequently with buffers often use this equation to calculate the pH of buffers. In doing equilibrium calculations, we have seen that we can normally neglect the amounts of acid and base in the buffer that ionize. Therefore, we can usually use the starting concentrations of the acid and the base components of the buffer directly into equation 17.9. Buffer capacity and pH range. Two important characteristics of a buffer are its capacity and the effective pH range. Buffer capacity is the amount of acid or base that the buffer can neutralize before the pH begins to change to an appreciable degree. The buffer capacity depends on the amount of acid and base from which the buffer is made. The pH of a buffer depends upon the Kca for the acid and the relative concentrations of the acid and base that comprise the buffer. According to equation 17.5, for example, the concentration of acid for a 1 liter solution that's 1 molar in acetic acid and 1 molar in sodium acetate will be the same as for a 1 liter solution that's 0.1 molar in acetic acid and 0.1 molar in sodium acetate. The first solution has a greater buffering capacity, however, because it contains more of the acid and its conjugate base. The greater amounts of the conjugate acid-base pair, the more resistant to a change in their concentrations and hence to the pH is to change. The pH range of any buffer is the pH range over which the buffer acts effectively. Buffers most effectively resist a change in pH in either direction when concentrations of weak acid and conjugate base are about the same. From equation 17.9, we see that when the concentrations of a weak acid and conjugate base are equal, then the pH equals the pKa. This relationship gives optimal pH of any buffer. Thus, we usually try to select a buffer whose acid form has a pKa close to the desired pH. In practice, we find that the concentrations of one component of the buffer is more than 10 times the concentration of any other component, then the buffering action is poor. Because the log of 10 is 1, buffers usually have a range within 1 positive or negative 1 pH unit of pKa. That is, the range of pH equals the pKa plus or minus 1.